Welcome back. So we'll continue our discussion on this eigenmode analysis of tower and nacelle in combination. So we have started with the static beam equation. Then now we are moving to the dynamic beam equation, and where we can estimate the kinetic energy. And this is what the last time we stopped, where the kinetic energy expression would contain the component from the tower and then the component from the nacelle. Both these units, both these units have certain mass, so that is why they are kind of also exposed to this dynamic loading due to the wind forces and other thing. So now going through this particular analysis, if you see this kinetic energy expression here, what we have taking care of the two component, one coming from the tower and then one coming from the nacelle. Okay, so these two components we consider, and so what we have is, now we can write omega square by 2 E naught m tower by L to the power 5 0 to L4 x4 dx m nacelle. Now further simplification, what we can have is that omega square A naught square by 2 1 by 5 tau nacelle. Now this is what we get for complete kinetic energy. Then elastic one, what we have half of 0 to L I A naught square by L dx. So we have A naught square by 2 EI 4 by L4 into L. So that's gives us A naught square by 2 EI 4 by L cube. So this is elastic potential energy and the kinetic energy that we have. So now if equate the kinetic elastic potential energy we have is that omega square m by 5 plus m nacelle equals to 4 EI by L cube. So this is what we get. So that's an so from here one can estimate the frequency of these things, the frequency of oscillation by considering them. So these are, I mean, if you look at it, so here the, I mean, one can kind of estimate this is an sort of an effective mass of that tower and the nacelle in total. So the oscillation frequency can be estimated. And why these are important? Because these are important to estimate the frequency of oscillations and then trying to find out what could be the natural frequency of that structural element. And since these are exposed to wind loading, so there could be effects, or I would say that the structural design consideration would be very, very important. So the, I mean, the complete procedure, if you think about, see, initially we were looking at it, the what could be the estimation of the axial force or the thrust and the effect of the number of blades and all these things. That's what, because of the wind and the rotation of the blade, you estimate the forces and how much power you can convert. So essentially, the wind energy in the wind, you try to convert to the power. But obviously, through the calculation of the power coefficient, thrust coefficient. But those forces are acting on the body of this system. That means the rotor blades, that's a rotating component. Then you have nacelle, which houses all the electrical component, gearbox, all other accessories. Then you have the tower, which is a very important element of this. So the any structural analysis requires the force acting on the body, and the force are coming from the wind. One way you can think about, or one can think about, this is a nice example of fluid structure interaction problem. You have a force which are coming or arising due to the wind. Now, and then different components of the whole turbine unit, they are exposed to different kind of loading, and that loading would dictate the design. And obviously, when you talk about that design, it also important to understand the material properties like E, I, and all these things. And then deciding the material is important, which material can resist how much forces and this kind of loading patterns and all these things. Um, so uh, that's where the I mean this analysis becomes important. Now later on, what you can see that we'll be discussing about the linearized system of considering this analysis, structural analysis, and considering the wind forces. There are not only wind forces, there could be wind shear effect, there could be ER effect, there could be other effect. Okay. Now, what see how the site and weights are weight of turbines are kind of, so you can see some example like let's say if tower height is 120 meter. So this is which is 1.8 megawatt power output. Then you can see their blade length R is 45 meter. Then you have the nacelle weight which is around 75 ton. Then 3 blades weight up to 40 ton. So you can see this total gives 115 ton, and you have tower height of 152 ton. So that kind of gives you an idea about. There is another one which you can have, that is tower height of 105 meter. This uh, Vestas V164, which is 9.5 megawatt. Then blade height is 2 meter, which is R. Then you have nacelle weight 390 ton. You have 3 blades weight on of in total, so almost close to 500 ton. Then you have tower weight, which is approximately 400 ton, and you have base diameter, which is roughly 6.5 meter. So you can see different these things, what you call the site, and but there are other turbines their uh, nomenclature and things would be different. Um, Now, when we talk about these towers, so what is important is to talk about this deep and soft towers and other things. So we can talk about steep and soft towers. Mm, so we'll be able to find out the lowest extraction excitation frequencies. So lowest excitation frequencies. Okay. So we have already discussed that 1P, which means uh, this is a rotor rotation frequency, which one can say blade excitation or blade asymmetries. Okay. BP is blade passing frequency with number of blades. Then we have tip speed ratio, which is lambda, that is R omega by U infinity, where radius R and wind speed U infinity. So this is that. So what we have, W1P would be omega which is lambda to infinity by r. And similarly, WBP B dot omega, that means B into lambda u infinity by r. So which means we always have BP into W1P. You can see W1P typically varies with wind speed. One can think about like there would be no problem if W, WBP become equal to tower eigenfrequencies. So we have to avoid with A, tower design, and B, controller design. So essentially what one has to do, this rotation frequency and the blade passing frequency can be equal to the tower eigenfrequencies. But importantly, one has to avoid the resonance. So while designing the tower and the controller, one has to be careful that this blade passing frequency and rotation frequency should not come in resonance. Otherwise, they can be equal. And so now what, so these are typical constant while doing the structural design. And if there are resonance that occurs, and which is always a likelihood possibility, because there could be catastrophic failure of the whole unit. So it is always a good idea to avoid those kind of resonance, occurrence of resonance, things like that while doing the design through analysis. So as I mentioned earlier, this is quite interdisciplinary in nature, and also it is quite a bit of involved in a sense that this is a real example of fluid structure interaction problem. Now, what we can see, let's say, for let's say we have a let's say some given operational speeds. Let's say 1 radian per second, 2 radian per second. So let's say given range of the tower can be operated in the frequency domains. Okay. So A, you can see there could be soft, which is if its lowest eigen frequency W tower is in region A. Then we have soft if W region B, and C, it could be steep if omega tower is in C. That means it is higher than rate passing frequency. In this case, all eigen frequencies are omega BP max. Okay. So what one can draw, this is for varying omega. You have 0. So you can have omega 1p mean, omega 1p max, and then we can have 3p min, omega 3p max. So this is a zone A, this is zone B, this is zone C, which is typically steep. This is soft steep. This is soft. Okay. So the mechanical resonance frequencies would be designed to be in these regions to avoid being excited. So that means when this design has to be done, then one has to take that into consideration, that where the mechanical resonance frequencies to be fallen so that you can avoid this resonance. So whole idea of all these analysis or the discussion is that you have a rotor blade which is rotating. So once it rotates, there would be a rotation frequency. Then there could be a blade passing frequency when the blade passes for a single revolution. Since these are dynamical system, they kind of exposed to some dynamical loading and their typical eigenvalues, eigenvectors, and things like that. So in the design, one has to take that into consideration that these are the things are going to be very, very important in a sense. So, I mean, one can see an example which, like, mm, that the one that Vestas 160p164, where we have already seen that, let's say, 1 rad per second. This could be 2 rad per second, where you have lambda equals to 8, r equals to 80 meter, u infinity equals to 10 meter per second, omega equals to 1 rad per second. So you'll have a variation of omega over u infinity like this. Okay. So and then similarly one can see the variation with u infinity, the lambda that goes up, comes down, stays there. That is lambda optimum. So this is between, I mean, essentially 1 rad and 2 rad per second. So this would be 2 rad. This is the line for 1 rad per second, like that. So this is an example where you can see how these things varies. Okay, so we'll continue this discussion in the next session. Okay.